Hello. Here we'll continue looking into linear maps. Adding them and adding their corresponding matrices. The operation of addition is possible if we have linear maps between the same vector spaces. So we have to start with n vectors, we transform them into m vectors, and we have two such transformations called f and g. So each of them is linear, meaning that f is additive on a sum of vectors. It is the same as the sum of values, and preserving scaling. And the same for g. G is also additive and preserve scaling. So what we're going to do is to first introduce the way of adding two linear maps. Well, we can add really two maps at all, so the sum of them is again going to be a map from n vectors into m vectors. And what we need to do is to tell anyone what do we say, what do we mean by the value of this new map on a vector. And that is easy if we know f and g. We can compute f on v, we can compute g on v. These are two vectors in this coordinate vector space. There are two vectors of length m. We can add them up. So that is the definition of the new transformation, of the new linear map transforming again n vectors into m vectors. What is good about this new transformation? It is going to be linear again. So that is an example of an abstract proof. We can prove that if f and g are linear, then their sum will be linear as well. And the proof will consist in verifying two properties which make something linear. The first property is that the new map we have, this sum of f and g, is additive on the sum of two vectors. It is the sum of values. So let's see what happens. We just will follow with what we have. And first, what we have is the definition for any vector. What is to be the value of this new transformation on the sum? Sorry, on any vector. And the definition says we have to compute v on this vector, on the input vector. We have to compute g. So we have to compute f, we have to compute g, and then we have to sum them up. That is just by the very definition of this addition of transformations of linear maps. Then we can use additivity property for each of the maps we sum. F and g are separately linear, and so we can simplify, or rather rewrite, these two values. The first will become the sum of values of f, and the second the sum of g values. And then what we can do, we can rearrange the summands and put f and g evaluated on the same input vector u together. And we will have f on u plus g computed on u, and then we'll have f computed on v plus g computed on v. But that's what we call the value of the sum on u and on v. And so we have this answer. which really is saying that f plus g is additive. Its value on the sum of two vectors is the sum of values. The same for scaling. If we want to see that this transformation, which is the sum of two linear transformations, preserves scaling, we just need first to write by the definition how we compute this. And we compute it as a sum of values of f and g separately, then use the fact that f and g preserve scaling, so put scalars out of through f symbol. This is v and g. And then distribute in reverse, combine it into one scaling of a sum. But then finally notice that this sum is nothing but the value of f plus g on v. And again, we have what we wanted, scaling preservation this time of this transformation f plus g, which shows together with the first one that it is linear. So since it is linear, we can talk about its matrix. Each transformation we sum up, f and g, they have their own matrices. So let's call them names. B will be the A will be the matrix of transformation f. So f evaluated on any vector is the result of multiplying this vector with matrix A from the left, and B will be the matrix of transformation G, again meaning that G has this shape. So we want to compute the matrix of the sum. If we write what the sum is, by the very definition on any vector, it is the sum of values. And since each of the values is given by matrix multiplication, we can write it this way. And then it's more than natural to call the matrix of the sum A plus B. So that is just the name for the matrix which we are about to compute. That is the matrix of A plus G. Whatever it is, we just call it A plus B. And now we're going to see what is A plus B. Because we know how to compute matrix of any transformation. So the matrix of this transformation is column by column, the result of applying a transformation to basic coordinate vectors. That is the first column applying to the first coordinate vector. When we apply the transformation to the second coordinate vector, we get the second column, and all the way till the last. So that is the general recipe of computing a matrix. Now let's put it into use. Now we have to see what the answers are for these columns. But yeah, we have the definition of what the sum of our f and g on any column is. That's the sum of the values of f and g on the same column. So that is the answer for column number 1. And I'll skip all the middle and write the answer for column number n, the last one. But this first ingredient in the answer for the first column is f evaluated on the first coordinate vector, and that is the first column in the matrix A. So A is just to put the dimensions into the story. A is of size m by n, and so is B. when multiplied with n vector, it turns it into m vector, as transformations should do. So that A, if we just call it, if we write it in elements, it will have m rows and n columns, and so will B. And here we have the first column of A, and here we have the first column of B, and so what we are dealing with is, what we are seeing is the sum of columns. And the coordinates of this sum will be just pairwise sums of the components of the matrices. And that is a result of summing up in the first column, but everywhere else it's the same process. We are summing the matrix entries according to their positions. So that is what we can call the sum of A and B. That is what we called actually the sum of A and B. That is the definition again of how we sum matrices. So if we call its matrix entries ij, then a compact formula for how to compute the entry in this sum of matrices in the position I and j in i's row and jth column, and that will be just the sum of same positioned elements in the matrices we add up. So that is the recipe for computing matrix entries of the sum. And as just the notation goes, we have a nice property for this sum of matrices when we put it together with multiplication by vector. So if we take sum of two matrices of the same size and multiply it with a vector, it's the same as to do it in a different way, multiply matrices with the same vector first and then add. So that is an instance of this distributivity law, but now for matrix and vector multiplication. More to come later.